Thanks. So let me begin just by thanking the organizers for this wonderful workshop and also acknowledging my collaborators. So Sean Hartnell at Stanford with me and Shankar Desarma at Maryland. Okay, so this talk is essentially about transport properties, and that means that all that we want to do is compute the coefficient in Ohm's law. Okay, so it's simple enough. Certainly to measure experimentally, this is very elementary. Now, more generally, we'll be interested in not only electrical transport, but in thermoelectric transport. So we apply electric fields and temperature gradients in some combination, whatever we want. And then we measure charge and heat currents, J and Q, that flow through the sample. And then we're interested in the linear response coefficients that show up in this matrix right here. Okay? So our goal is to compute these things for a metal. Now, if you go and look up in Ashcroft and Merman, there's a prescription for how you compute these things. And schematically, the story is that resistivities, which is just 1 over conductivity, but also thermal conductivity as well, are essentially just governed by some scattering time, tau. Okay? Now, in a metal, there are a lot of different things that could contribute to this scattering time, which is roughly the time it takes for a single electron to sort of move from traveling in this direction to traveling in this direction. Okay? So in a typical metal, we would have impurities, we would have phonons and other electrons. And any given electron could scatter off of all of these different things. And to explicitly compute this scattering rate tau is actually quite annoying because it depends on a lot of very specific sample-to-sample properties, not simply material properties. So typically, what we would do is just ask, can we at least get the temperature dependence of the resistivity down? So here I've listed the conventional temperature dependences of all of our conventional scattering mechanisms and how they would contribute to this scattering time. Now, the second part of the conventional law is that in a metal, you have all of these things going on at once. So a real metal will have multiple electrons in it, and it will also have phonons as well as impurities. So we'll have some contribution coming from all of these channels, and we just add them all up. So this goes by the name of Mathiassen's rule. And that's a very simple story. It's essentially entirely semi-classical, but it's actually quite successful for most metals out there. Okay? And if you really want a quantitative success story of this old formalism, that would be the Wiedemann-Franz law. Okay? So if you measure the electrical and the thermal conductivity of the same sample, then as long as it's a good Fermi liquid with essentially conventional scattering mechanisms like disorder, then the ratio of the thermal to electrical conductivity should be a universal number. And this number will not depend on any sample properties like carrier density. And indeed, if you look at this plot, I think we have here 8 orders of magnitude in carrier density. And all of these metals come within 15, 20% or so of the Wiedemann-Franz law, many of them much closer than that. So let me make one more sort of side note, which is that experimentalists don't measure thermal conductivity the way theorists would. And I assume this is some historical accident. But this is the coefficient that experimentalists measure. Okay? So this kappa doesn't come with a bar on it. Oh well. Anyway, so this is an old success story of our theory of transport in metals. But there are also a lot of things about transport that we don't understand. Okay? So one big puzzle that we don't understand about transport that I won't have so much to say about today, but this is just to point out that there are things we really don't understand. This is a plot that's maybe slightly hard to read, but what it's doing is comparing the coefficient of T-linear resistivity in a number of non-Fermi liquids. Okay? So you'll notice that T was one of the scaling laws in the zoo that I showed you earlier, but we don't think it's relevant for a lot of these systems because sometimes these T-linears can occur at rather low temperature. And if you fit them to the crude Drude formula and you try to extract out what is the time scale in the resistivity, in all of these sort of bad metals, things that are not described by our conventional Fermi liquid theory, they seem to have a scattering time which is h bar over kBt. So this is this Planckian limited scattering rate. Okay. So this suggests that there are scattering mechanisms beyond what we understand, things that are not captured in our conventional approach. But there are also puzzles that probably have somewhat more conventional resolutions. So by this I mean metals where we probably don't need to invent new theoretical approaches. We just need to apply the ones that we already have in a smarter way. So these are things like low-density oxides, like strontium titanate, where we can find very robust T-squared resistivity with a single small Fermi surface. Now, I had in the earlier zoo of scattering mechanisms that a T-squared would come from electron-electron scattering. But if you look more closely, that's not any old electron-electron scattering. There are only certain kinds of electron-electron scattering that could contribute to this T-squared, a point which will become clear shortly. And none of the existing mechanisms for T-squared actually apply to this material. But nevertheless, we see a very robust T-squared. So hopefully, I won't have too much more to say about experiments, but I just want to emphasize that there are a lot of things about transport that we still don't understand. And so the point of this talk will be to try and look at the old approach to transport and to essentially try to uncover some new mechanisms that have not yet been elucidated. Okay, now both of the things on the previous slide likely involve strong electron-electron interactions. So it's worth asking a little more carefully, how could electron-electron interactions contribute to the resistivity? Now, let me suppose for the moment that I have some interacting metal, but completely translation invariant. Okay? So I just sort of write down, like Peskin and Schroeder, my effective field theory for the metal. It's homogeneous, translation invariant, and it's an interacting quantum field theory. And then I try to compute the conductivity of this system. Now, before writing down any equations and doing a lot of work, I can tell you that the answer is infinity. Okay? And the reason that the conductivity is infinity is that here I'm standing next to my metal at rest. But now, because this is a translation invariant system, it has a conserved momentum. So I can go ahead and not look at a state that has 0 momentum, but look at a state that has finite momentum. And as long as I have a finite charge density, this finite momentum state will have a charge current on average. Okay? So this operator will have an expectation value. In the absence of any electric field, this still holds. So I conclude that the conductivity is infinite if the collisions in the system, whether they're electron-electron or electron impurity, if those collisions are not relaxing momentum, the conductivity is infinite. Okay? Now, many electron-electron collisions, especially in a material like strontium titanate, are momentum conserving. And so, if we see a T-squared resistivity in this material, and we think it's coming from electron-electron collisions, that's actually very non-trivial because none of those collisions are actually relaxing momentum. So in principle, they should not contribute to the conductivity at all. Okay. Now, one more simple cartoon before I sort of get into the theoretical weeds a bit. You might think, if momentum conservation is really important for understanding transport properties in a metal, then why don't instead of just looking up this Drude formula in Ashcroft and Merman, why don't I instead start from Newton's laws? Okay. So now I'll write down my force balance equation, and this force balance equation will consist of two pieces. So this term is the Lorentz force, right? If I apply an electric field to a charged object, it experiences a force. There's a thermal analog of the rho times E term. And then I will also generally have some momentum relaxation. And I have to have something else here, right? Because if I don't have anything else here, then the conductivity would be infinite. And that's following from the fact that my force balance equation doesn't hold and there's no static solution. Okay. Now, I've parameterized the momentum relaxing term in this kind of simple way as a coefficient gamma twiddle times the velocity. Let me just state that a proper definition of velocity would imply that, at least for sufficiently small gamma twiddle, charge current would be the density times the velocity, and the heat current would be temperature times entropy density times velocity. Okay? And so we arrive very easily at the thermoelectric conductivity matrix. All of the conductivities are controlled by the same scattering rate, gamma twiddle. This isn't a rate, it has other units too, but you know, there's a rate hidden in there somewhere. And then we have this matrix of coefficients. And that's sort of reminiscent of the Wiedemann-Franz law, right? The same scattering rate controls both sigma and kappa bar, so it would cancel out. But the problem is that the temperature dependence here is all wrong. Okay? So in a conventional metal, S would scale linearly with temperature, and this would predict that kappa bar over sigma t scales like t squared. Okay? Then we haven't yet done this bar removal on kappa bar, which would shrink it even further, in fact to 0 in this cartoony model. So, you know, I started from a very simple place, and I've completely, I found something completely different than the conventional phenomenology. And so you might ask, you know, where is this one? Well, okay, you know where this one is coming from, I suppose, but, you know, why is this not at all looking like the old phenomenology? Is this one never valid at all? You know, if they could both be valid, how do you cross over between them? And one other question that we should also ask is, you know, what is this scattering coefficient gamma twiddle? Can we relate it to what would have been the scattering time tau, you know, were the Wiedemann-Franz law valid? Okay. So these are all questions that I'll at least sort of highlight the answers to in the rest of the talk. Okay. So in this talk, we're going to assume that kinetic theory is valid. Now, this is not because I think kinetic theory is valid for all metals, but this will be a helpful approach because, first, it will necessarily recover for us a lot of the Ashcroft and Merman phenomenology, which did start from this equation. But we'll also see that if we treat this equation a little bit more carefully than has been done in the past, we'll be able to uncover a lot of new phenomena that had been missed. Okay? Okay, so what does this equation mean? Well, the left-hand side tells us that if we just had a bunch of electrons doing their own thing, they would follow the trajectories governed by the classical Hamiltonian mechanics, okay? Just for a single particle. Now, this is a sensible thing to do only on sufficiently long length scales such that the Fermi wavelength is very small, and so quantum effects can be neglected. On the right-hand side of this equation, we will perturbatively introduce a collision operator that has a very nasty form in general. Okay? But there's a prescription for how to compute it. You can roughly think of it as you know, the lifetime of each individual particle. Okay, so it's a very complicated equation. It's extremely nonlinear. It's an integral differential equation. And nobody can really solve this thing exactly. So we have to make some approximations and or simplifications to go any farther. And so the next couple slides may be a bit technical, but the sort of key highlights to keep in mind are, first, I showed you that the conductivity would be infinite in the absence of momentum relaxation. So you could ask, can we make sure that momentum will in fact relax before we go any farther, because otherwise it's all a waste of time. So if the electron-electron collisions are momentum conserving, which I'll assume henceforth, then the only place, and I won't account for phonons for simplicity, that's already in the textbook, then the only place that momentum can relax is in this force term. Okay? So I could add an external magnetic field if I want. That will show up on one slide in maybe 10 minutes or so. I can add electric fields and temperature gradients. This is one way that I can dump momentum into the system. And I can also break translation invariance with an inhomogeneous chemical potential. Okay? So we'll have to account for this term carefully if we want to properly compute the conductivity. Okay? All right. Now, the next question that we should keep in mind, the answer to this question will basically be the punchline of the talk, is how do electron-electron collisions modify transport? Put more simply, let me start as a theorist with metal that has no Coulomb interactions. Okay? So I write down my Hamiltonian and I just delete the electron-electron interaction terms by hand. And I run the machine, I compute the conductivity, and then I rerun the whole machine without deleting the electron-electron terms. And which answer is bigger? If I computed the conductivity with interactions and without interactions, which one is bigger? Okay. Now, the last thing to keep in mind is that the kinetic equation was highly nonlinear, but we're only interested in linear response properties. So let's just linearize the equation of motion. We linearize around equilibrium, and if I just peel off this kind of singular function near the Fermi surface, then the function phi that I'm solving for is very well behaved. Okay, so I'm just going to write down some equations for phi and solve them. Okay, now I'll try to put a lot of this under the rug and just sort of show you the schematic outline of how this goes. So you linearize the kinetic equation, and you get two kinds of terms acting on phi. One of them comes from the collision integral being linearized. These will be dissipative contributions. Okay? And then there are also contributions coming from the streaming terms. Okay, I probably didn't need to write this as a convolution because there are only derivatives in L, but whatever. And then the problem is sourced by an electric field that couples to the charge current and a temperature gradient that couples to the heat current. And these J and Q vectors are not arbitrary. Really, you choose a sensible inner product. It's the natural one. And it turns out that the actual charge current that you measure is just the inner product of J with phi. The heat current is the inner product of Q with phi. And so, roughly speaking, we just want to invert this matrix W plus L on the right-hand side, and then sandwich on the left with J and Q. We already have J and Q on the right, and this is our thermoelectric conductivity matrix. Okay? So all we have to do is invert this very infinite dimensional matrix, and then we're done. Okay, now the first thing that I should comment is that it's really helpful to treat disorder perturbatively. Then there's a very sensible, you can integrate out disorder accurately, and you essentially get a homogeneous effective collision integral. For the next couple slides, I'll sort of be sloppy about what that effective collision integral is, and then I'll come back and treat that much more carefully. Okay? So we can integrate out the disorder. We get an effective collision integral that now only depends on the momentum indices in our kets. And the next thing that we can do is essentially realize that our effective collision integral will be block diagonal. And so we really only need to keep track of a small set of radial basis vectors. Okay? Now, our inner product that we choose turns out to have a very nice property, which is that this basis vector has length t over tf to the n. So if we're not interested in Fermi surface smearing effects, we actually don't need to keep track of this infinite tower of vectors. It actually truncates to a finite dimensional set, so long as we're willing to throw out high order corrections in t over tf. And I haven't said anything about interactions, so you can treat interactions non-perturbatively, and still the problem is reduced to this finite dimensional problem. Okay. So the effective collision integral, if I essentially assume that the disorder is either short range enough or the interactions are weak enough, I can neglect the collision integral of the electrons when I calculate the electron impurity scattering rate. Again, I'll come back to that issue soon. But for the moment, let me ignore that. So the electron impurity contribution to the collision integral is really a single particle effect. This is very conventional. And we find Mathiassen's rule in the collision integral. Okay? So very conventional so far. The only thing to keep in mind is that these are matrices, no longer scattering times. So we have to be careful that, these matrices add, but that doesn't mean that their eigenvalues all add. Okay? Now, one can show that to leading order, this WIMP is a temperature-independent matrix proportional to the identity. If you want to compute the thermoelectric conductivity alpha, you need this subleading correction, but I won't talk about that much. This W, well, it has a null vector associated with momentum. Okay? So analogously to how there was a vector J that encoded the charge current flowing in the system, there's a vector P that encodes the momentum flowing the average momentum in your distribution. And this vector P is a null vector of the collision integral. That's what it means to have collisions that conserve momentum. And we'll parameterize with little gamma the typical value of the remaining eigenvalues. Okay? So capital gamma is electron impurity scattering rate, and little gamma is electron-electron. That's just to avoid lots of subscripts as we go through. Okay. So now at this point, we're ready to actually show some conductivities. And to do that, we're just going to say that we really don't care about thermal smearing of the Fermi surface. We really just want to ask, where do the electron-electron collisions come in strongest? Okay? So we're going to truncate this tower of basis vectors to only the lowest two. The only sort of sleight of hand that we're going to do is this little gamma typically would be t squared in an ordinary Fermi liquid, but we'll just resum all of these t squared corrections. Okay? So we'll just treat little gamma as temperature independent until the last step. Okay? And the punchline is that the conductivity doesn't care at all about the electron-electron scattering rate. Okay? But the thermoelectric, the thermal parts of the matrix do. And in fact, you'll notice that both kappa bar and alpha are a sum of a red term and a blue term. The red term in both of these equations corresponds to essentially the textbook formula weighted by the fraction of the collisions that are off of impurities. That's the heuristic interpretation of the answer. So kappa bar is just the Wiedemann-Franz law, conductivity times pi squared t over 3, weighted by the fraction of impurity momentum relaxing collisions. Alpha is proportional to the Mott law, something very similar, again weighted by the fraction of electron impurity scattering events. The blue terms correspond to these hydrodynamic, or these, let's say for now, these Newton's law conductivities. Okay? So these blue terms correspond to what you would get if you wrote down the force balance equation and you said that all of the conductivities are proportional to the same scattering rate, but then we have charge density and entropy density weighting sigma and kappa bar and alpha. So if you go through and you look carefully at what all of these coefficients are, you find that these blue conductivities, which dominate when little gamma is very, very large, these are precisely the sort of momentum-limited conductivities. Okay? Now, what experimentalists measure, just to conclude this part, is the kappa without the bar. And that turns out to just be the Wiedemann-Franz prediction multiplied by the fraction of electron impurity scattering. Okay? So this is sort of a very simple resolution to my first question, which was which one of my two transport cartoons is right. And when electron impurity momentum relaxing scattering dominates, the textbook approach is right. And when the momentum conserving collisions are more important, we get this transport physics governed by essentially Newton's laws, governed by momentum relaxation. Okay? All right. One more quick comment. Well, okay, two more. First, I've assumed an isotropic Fermi surface here, but beyond that, I haven't assumed anything about the dispersion relation. Okay? And so these results, would apply both to the Fermi liquid in graphene, gallium arsenide, et cetera, any system with an approximately circular Fermi surface. Now, another prediction, which would also apply to all of these systems, okay, is if you turn on a background magnetic field, then you get a new scattering rate in the problem, which is simply the cyclotron frequency. And now you can ask, how does this Lorentz number change as a function of both omega c as well as these electron impurity scattering rates? So we have another very simple formula for what happens in this case. You get this ratio of these three scattering rates. And if you just plot it, what you see is that once you turn on a magnetic field, and once this cyclotron frequency becomes larger than the impurity or momentum relaxing scattering rate, this Lorentz number becomes a non-monotonic function of temperature, or more precisely, electron scattering rate. And once again, this is a simple formula that, in principle, you could fit to experiments. For example, at low temperature in gallium arsenide. Okay. So this is essentially the thermoelectric part of my story. Just to sort of emphasize to you that electron scattering plays a somewhat special role in transport, just because these are momentum conserving scattering. Okay. So now I want to return to this question of what is the actual electron impurity scattering rate? So if I have strong electron scattering, I can't just assume that the electron impurity scattering rate is some temperature-independent constant and then forget about it. Actually, the interactions can play a profound role on what the electron impurity scattering rate is. Okay? So within the kinetic approach, this means that I need to evaluate this object, which is maybe a little bit frightening. In a more physical picture, what we're essentially asking is the following. So we have some potential, some inhomogeneity, which is smooth on a length scale, which I'll denote as c. And keep in mind that this scale should always be very long compared to the Fermi wavelength. Okay? Otherwise, the kinetic approach just fails. Now, so far, we've essentially assumed that the mean free path for electron-electron collisions, LEE, is like the size of the screen, or the size of the screen in the chalkboards. It's so big that this individual electron really doesn't see anything else as it moves through this inhomogeneous landscape. And so it's already completely changed its direction by the time it sees another electron. That's at least the sort of cartoon you should have in mind. Okay, but that's not necessarily the case. Especially when you have strong electron-electron interactions, it should be possible in materials like graphene and gallium arsenide, where disorder is also very long wavelength in general. It should be possible to find systems where this effective mean free path, the length in between two electron-electron collisions, is actually comparable to this puddle size or even shorter. And then you can't ignore this collision integral anymore when you evaluate the electron impurity collision time, and you will really have to treat interactions non-perturbatively as we evaluate the electron impurity scattering rate. In field theory language, what this will amount to doing is calculating the spectral weight of whatever operator couples to the inhomogeneity. So in this cartoon, so far I've been talking about the potential terms in the Boltzmann equation. These are like an inhomogeneous chemical potential. The operator this couples to is the charge density. And so what we're computing here is the spectral weight of the charge density operator. And we'll use kinetic theory to essentially find the semi-classical approximation to this spectral weight. Okay? All right. So now to evaluate this object, we need a tractable model of kinetic theory. Notice that, so what is this L sub k? Well, it's essentially just the velocity, so the p derivative of the dispersion relation, dotted into k, the wave number. So this breaks rotational invariance, and we'll essentially need to couple an infinite number of angular harmonics together to compute this inverse. So we're really looking for a very, very crude model where this might actually be tractable. So really this is due to Levitov and friends, but they realized that this very simple model of a 2D Fermi liquid where you throw out all of the radial smearing of the Fermi surface and you just approximate the kinetic theory by essentially the wobbling of an infinitely sharp Fermi surface. In this model, it's actually analytically possible to compute this full inverse. Okay? So now we can evaluate all of our electron impurity scattering times non-perturbatively in the interaction strength. Sorry, there's one more thing that you need to do before this becomes analytically tractable, which is you need to make a sufficiently simple choice for the collision integral. So this is one very simple choice that you can make. This is called the relaxation time approximation. And what it's saying is that we conserve charge and we conserve momentum. So our collision integral, if you just plug in either the zero harmonic, so radially growing and shrinking Fermi surface, or the n equals plus or minus 1 harmonics, just translating the Fermi surface, these things never relax. This is simply charge and momentum conservation. But all of the other harmonics will relax, and they'll relax with some universal rate. With these assumptions, you can analytically calculate essentially all of the Green's functions in this kinetic theory. Okay, so now we just plug these Green's functions into this machinery that I outlined, and this is the answer. So what I'm plotting here is the resistivity normalized by its residual zero temperature value. That's why it goes up to 1 here. And the x-axis here corresponds to the puddle size of the impurity divided by the electronic mean free path. Okay? So 0 corresponds to 0 temperature because the electronic mean free path becomes infinite. And this axis you can think of as a proxy for, let's say, t squared, or t squared over log t, strictly speaking. And what we find is that actually interactions very dramatically decrease the resistance. Okay. Now, this effect has never been seen in experiment, or at least not, I think, that anyone is aware of, at least in a bulk transport measurement. There are a few experiments that have been very specialized that have measured this kind of effect in a channel setup. But in terms of a bulk resistivity of the kind that we're interested in, this effect is really never seen, which is at some level surprising because this is quite far from the hydrodynamic limit. So at this point, the electronic mean free path is 5 times longer than the puddle size of the disorder. This is a regime that in principle is very realizable in graphene. And depending on the specific details of your microscopic disorder distribution, you could get basically a factor of 2 reduction, or worst case, a 25% reduction in the resistivity. Okay. But these effects haven't been seen, and this sort of got me thinking, are there other loopholes or shortcuts that get around this effect and look more conventional? Okay. So in particular, this is the asymptotics of this curve are 1 over temperature squared. Okay. Now it turns out that if you couple disorder, or if you add disorder that couples to different operators, so instead of the density, you now couple to the current operator, for example. This is what I would crudely call the random magnetic field. Then you find actually the opposite effect of this. You find that now the resistivity goes up as you increase electron-electron interactions, and this ends up being a very beautiful t-squared. Okay? Already by the time the puddle size is comparable to the electronic mean free path, the disorder has increased by a factor of almost 3. And you see that this is not a perfect Mathiasson rule, but it would probably deceive a lot of experimentalists. That's my guess. No offense, but so you get a very deceptively simple answer that mimics a conventional t-squared, but this is a very unconventional mechanism for it that I'll explain at the end of the talk. Okay. So the punchlines are that this very simple model elucidates for us that firstly, once you treat interactions seriously and you ask how do interactions modify the electron impurity scattering time, the answer is actually very sensitive to even very elementary microscopic details. Okay? And you can get parametrically different scaling behavior depending on the kind of disorder that you have. So this is rather different from in the ballistic limit, these are all just some temperature independent number and we don't really care. That's why all disorder just gets thrown into the residual resistivity in the textbook story. Okay, but here you can't do that. And the other thing worth keeping in mind is that these interaction-induced corrections to transport are not negligible. Okay? Even when you're very far from the regime where you would expect electronic interactions to be important. So you can measure, quite noticeable effects on the resistivity even when you are in a regime that's quite weakly interacting. Okay. All right. So to explain what we just saw, what we're seeing here is essentially the onset of hydrodynamics in our Fermi liquid. Okay. So the conventional transport story sort of implicitly assumes that you have a bunch of electrons in your metal and they're all off doing their own thing. They never care that there's another electron in the system. At the end of the calculation, you just add up that you have n electrons. Okay, that's this collisionless limit. But what we're seeing is the onset of a hydrodynamic limit where you really need to treat the fact that you have interacting electrons seriously. And we'll see that what's happening here is essentially that you're replacing the single particle modes of the sort of conventional textbook approach with collective hydrodynamic modes. Okay? So in the kinetic equations, this limit's very simple to understand. If I write down the equations governing my, the harmonics of my fluctuating Fermi surface, so these are phi sub n, I get this hierarchy of equations, and the n equals 2, n equals 3, etc. modes are all decaying. Now, on long time scales, when this inequality holds, right, I can drop this term because that's negligible relative to this term. And so now I can actually collapse this infinite set of equations onto a set of 3 equations. I've just written 2 of them down because plus and minus 1 look kind of the same. The zero harmonic equation is simply conservation of charge, or the continuity equation. And the plus and minus 1 equations together form the conventional Navier-Stokes equation, linearized around equilibrium. Okay? So this is a very sensible and conventional result within kinetic theory. Okay. So as I mentioned, the proper way to think about transport in this system is that at very low temperatures, what was happening is that you hit the system with your external source and you excite the normal modes of the ballistic limit, which are just all of the quasi-particles that don't talk to one another. Okay? And these are those normal modes. And that's indeed the conventional theory of transport. You have a bunch of single particle excitations. They scatter through, at least the disorder part of the story. These single particle excitations scatter through your disorder landscape. This is a single particle quantum mechanics problem, so you get a temperature independent scattering rate. But in the hydrodynamic limit, the fundamental excitations are not of this form. The fundamental excitations will be sound waves. Okay? So these are ballistically propagating modes. They decay at a rate gamma s k squared. Gamma s will be proportional to the electronic mean free path. And we also have a diffusive mode. Okay? So in this simple model, this is all we have. We haven't accounted for radial fluctuations of the Fermi surface, which would include energy conservation. Okay? So we have, in this simplifying limit, 2 hydrodynamic modes. And it's really these hydrodynamic modes, and not the single particle excitations of the ballistic limit, that are moving through this inhomogeneous landscape. Okay? And it's the scattering of these hydrodynamic modes off of the disorder that's ultimately going to give rise to our new temperature dependence of the electron impurity scattering rate. Okay? So now we're finally ready to answer the question of, do the electron-electron interactions increase or decrease the resistivity that we measure? Okay? So remember, this is simply asking, the electrical conductivity itself, which only depended on the electron impurity scattering rate. How does that electron impurity scattering rate depend on interactions? So that's essentially amounting to how the interactions modify the spectral weight of the operator that couples to disorder. And if that operator has some overlap with a hydrodynamic mode, like a sound wave, then the disorder will actually, the interactions will actually suppress this spectral weight. Okay? And it will shrink as I increase interactions proportional to the mean free path. But if I have disorder that couples to a diffusive mode, okay, these diffusive modes have a spectral weight that goes like 1 over the mean free path. And this spectral weight blows up. Okay? One way you can crudely think about this is that if you're pushing a sound wave through the inhomogeneous landscape, you essentially have 2 conservation laws to play with. And one of the conservation laws is sort of eaten up by the fact that the current has to be conserved as you push it through the inhomogeneous landscape. And then the other one you can massage to minimize entropy production, but being able to massage it to minimize entropy production actually reduces the entropy production overall. In the diffusive case, you only have one conservation law, and you lose it just by the conservation law itself. So now, you apply a shear strain to your system, let's say. We're exciting diffusion of transverse momentum, or a shear velocity gradient. And the stronger the gradient is, right, that gradient is proportional to viscosity, or the stress tensor is proportional to viscosity times the gradient. Okay? And so as the viscosity becomes very small, the stress tensor itself becomes quite large. And basically, the fact that the stress tensor is scaling like 1 over LEE, and then contributes to entropy production squared, gives you this 1 over LEE at the end. Okay. All right, so let me make one point and then I'll stop. So I mentioned earlier that one of our transport mysteries was we didn't understand where this linear and temperature resistivity was coming from in a non-Fermi liquid. Now, these non-Fermi liquids don't just sort of come on their own in nature. They come as a part of a very complicated and messy phase diagram, like this one. Now, some parts of this phase diagram are fairly simple. For example, everywhere where you see blue here, this corresponds to what people would call a conventional Fermi liquid. You see T-squared resistivity. Nothing seems surprising. Now, the point which I would like to make is that it would be a bit odd. This phase diagram is measured, I assume, on one crystal. Presumably, the disorder mechanism, the physics of momentum relaxation, need not change all that much as I move, from one part of this phase diagram to the other. But so far, if we sort of apply a lot of the conventional approaches, it seems as though, in each part of the phase diagram, you're invoking a different scattering mechanism. We don't know what this one is, to be fair, but it would be unfortunate if we had to invoke a totally different scattering mechanism here than here. And so the point I would like to make is that, now we have new mechanisms for T-squared. This T-squared does not have to come, from Umklapp scattering. It can just be a conventional momentum-conserving collision between two electrons. And that's nice because we do have a lot of theories that have T-linear momentum-conserving scattering rates to describe this strange metal. Okay? So now that we have our mechanism, namely this sort of magnetic disorder, or more generally anything that couples to a non-thermal diffusion mode, what disorder that couples to these modes does is it converts a momentum-conserving scattering rate, at least heuristically, into the scattering rate that shows up in the conventional Drude formula. And so now we happily get T squared and T coming from one mechanism. So this is, of course, quite speculative, but I would just like to point out that these new hydrodynamic theories are not only valid in the Fermi liquid, but in principle would also be valid here. All right, thanks.
Well, thank you for this very physically motivated, methodologically clear talk, as opposed to many nowadays which are formal. Questions, please.
So you briefly mentioned it already, but maybe you can elucidate a little bit more how this approach compares to the normal single relaxation time approximation for solving the collision in part of the Boltzmann equation.
Almost everything that I was doing goes beyond that approximation. So all of this stuff, at some level, you could say that what we're trying to do from here on out, talking about hydrodynamic corrections to the electron impurity scattering rate, at some level, this is just trying to calculate, the impurity scattering rate that we would put in the collision integral. So you might say, oh, well, this is just sort of computing the effective collision rate you should do, and then I can take this scattering rate and do a single particle or a single time approximation henceforth. But if you do that, that's actually very inaccurate. The problem is, right, by the time that this W is not negligible, so basically by the time you see all of the interesting new effects, if I go back here, this W is now pretty big compared to this term. So you can no longer make this single relaxation time approximation by the time any of the new physics that I talked about kicks in. So all of this is sort of beyond a single relaxation time approach. But if you turn off the interactions, this recovers the sort of conventional relaxation time methods.
Very interesting talk. I wonder if you can put the resistivity in terms of some sort of viscosity in this hydrodynamic language, and
We can.
And if you can talk in terms of like turbulence, Reynolds numbers, and things like that.
Okay, so first we can put things in terms of viscosity. Basically, everywhere where you see, well, okay, so everywhere where you see this 1 over t squared, just schematically, you can replace that with eta. So that's at least if you just want the viscosity scaling. I didn't put them in the slides, but they're in these 2 papers. We do have formulas just written in terms of viscosity and other thermodynamic coefficients for what the resistivities are in all of the hydrodynamic limits. In terms of Reynolds number, the Reynolds number is always sort of infinitesimally small because these are linear response problems. I do think that turbulent electron fluids are probably not going to exist for a very long time. But that's a materials problem, not a fundamental physics problem. So.
Other questions? Yeah, I'll ask one. So regarding the puzzle number 2 that you listed in the beginning of the talk, the quadratic dependence resistivity in the case of a single small Fermi surface, so there's no clap, no de Beer scattering between the different Fermi surfaces. So what's the explanation of that?
Well, my proposal is this, that
And no hint on any orbital field type of scattering.
well, that's not clear. You know, these are complicated systems. They have lots of different kinds of disorder. Some people that work on this are telling me they're skeptical that there are differences in the disorder between samples that, you know, have different coefficients of this t squared. People are not convinced that it's magnetic disorder, but, you know, there is one subtlety here to keep in mind as well, which is that if you're just interested in this part of the resistivity curve, a lot of that physics can be very sensitive to microscopic details. So I didn't talk about this, but if you think about a slightly more non-trivial Fermi surface, you know, these curves can become non-monotonic. It's possible that there are just more complicated effects like that as well. But I think the point is that, you know, if you have these relatively smooth disorder potentials, interaction effects can be very significant. And I think it's very plausible that this sort of thing, whether it's magnetic or something else, a sort of qualitatively similar mechanism explains strontium titanate.
Fair enough. And then the rise of the resistivity with the lowering temperature in the case of potential disorder, would that be a precursor of the Gaussian effect?
This is it's in some sense the Gaussian effect in an inhomogeneous landscape.
All right.
This is more a physicsy question, but basically what you're trying to illustrate is the interplay between impurity scattering and electron-electron interaction, but the usual story is that Coulomb screening really kills electron-electron interactions in any of these systems. So do you have any, why would it not be so important? Or why would
Well, okay, I mean, one thing I would say here is that, you know, this is in some sense all built into this approach because all of this physics goes away at low temperatures, right? So all of these corrections are t squared. They're all related to irrelevant interactions in the Fermi liquid. If the Baire Coulomb interaction was important, I mean, there would be a number of weird things. Firstly, it's a long-range interaction, but they'd also be quite strong. So I think in gallium arsenide, the Baire Coulomb energy can be an order of magnitude higher, maybe factor of 20 higher. So, you know, already we have accounted for the fact that the Baire interactions are renormalized out.